Quasicrystals have long been one of the most enigmatic puzzles in materials science, captivating researchers with their seemingly impossible atomic arrangements. These structures, often described as the platypus of materials, challenge our understanding of how atoms organize themselves into patterns that are orderly, yet never repeat. For decades, scientists have struggled to explain how quasicrystals form and why they exist at all. But here's where it gets fascinating. Recent breakthroughs are finally shedding light on these mysterious materials, offering new insights into their formation and potential applications. And this is the part most people miss. These discoveries could reshape how we think about material design altogether. Since their accidental discovery by Israeli physicist Don Shechtman in 1982, quasicrystals have baffled chemists and physicists alike. Imagine atoms arranging themselves into chains of pentagons, decagons, and other complex shapes, creating patterns that stretch endlessly without ever repeating. To the untrained eye, it might sound like magic. How can something so intricate and mathematically precise emerge from the chaotic world of atomic interactions? When I first learned about quasicrystals, says Wenhao Sun, a materials scientist at the University of Michigan, my reaction was, that's insane. What makes quasicrystals even more perplexing is their defiance of traditional physical laws. Most materials, like crystals, rely on symmetry and repetition to achieve stability. Quasicrystals, however, exhibit what are known as forbidden symmetries. Take, for example, the five-fold symmetry found in quasicrystals, a pattern that cannot tile a flat plane seamlessly because pentagons don't fit together perfectly. This peculiar property was first theorized by British mathematical physicist Roger Penrose, who devised a set of tiles that could cover an infinite plane in non-repeating patterns. His work, published in Scientific American in 1977, laid the groundwork for understanding the theoretical underpinnings of quasicrystals years before they were discovered in the lab. Fast forward to today, and researchers are beginning to unlock some of the secrets behind these bizarre materials. In one groundbreaking study, Sun and his collaborators adapted a computational technique called density functional theory, DFT, to analyze quasicrystals. Traditionally used to study conventional crystals, DFT allows scientists to predict the properties of materials based on the behavior of electrons within them. However, applying DFT to quasicrystals is no small feat. Unlike crystals, which have repeating units that simplify calculations, quasicrystals lack periodicity, making computations exponentially more challenging. To overcome this hurdle, Sun's team employed a novel approach they dubbed nanoscooping. By extracting random chunks of quasicrystals, ranging from 24 to 740 atoms, they modeled the energy dynamics of these fragments and extrapolated their findings to the entire structure. Their results revealed something astonishing. Certain quasicrystals are thermodynamically stable, meaning their atoms naturally settle into low-energy configurations. This finding challenges the long-held assumption that quasicrystals are inherently unstable compared to their crystalline counterparts. Sharon Glotzer, a computational physicist also at the University of Michigan, but not involved in the study, praised the work as freaking awesome. She noted, until now, no one had successfully applied DFT to non-periodic structures. This is a clever leap forward. Michael Whittam, a physicist at Carnegie Mellon University, echoed her enthusiasm, adding that the stability result addresses a fundamental question. Why do quasicrystals exist in the first place? But the intrigue doesn't stop there. Another group of researchers, led by Brennan Sprinkle, an applied mathematician at the Colorado School of Mines, took a completely different approach to studying quasicrystals. Instead of working with individual atoms, which are too small to observe directly, they used commercially available particles called dynabeads. Thousands of times larger than atoms, these micrometer-scale beads allowed the team to manipulate and watch quasicrystal formation in real time using magnetic and electrical fields. As Sprinkle described it, the quasi-periodic structures seemed to fold out from some nucleation point like a three-dimensional snowflake. This experimental setup marks a significant advancement in the field, providing the first optical scale system for observing quasicrystal growth as it happens. Chad Merkin, a chemist at Northwestern University, hailed the development as a genuine advance in synthesis and application. While he cautioned that the mechanistic insights may not apply universally to all quasicrystal systems, the method opens up exciting possibilities for future research. Meanwhile, a separate team of Japanese researchers made headlines by reporting the first ever observation of antiferromagnetism in quasicrystals. Antiferromagnetism occurs when particles' magnetic moments alternate direction, typically seen in highly ordered materials. Its presence in quasicrystals, which lack such regularity, raises intriguing questions about the interplay between disorder and magnetism. Could this discovery hint at entirely new classes of materials with unique magnetic properties? The answer remains elusive, but the implications are tantalizing. Despite their allure, quasicrystals have yet to find widespread practical use. Their unusual structure places them in a sort of limbo, not as ordered as crystals, not as disordered as glass, and less malleable than the metals they're derived from. Nevertheless, researchers have identified niche applications. For instance, their poor conductivity and durability make them ideal for nonstick coatings on cookware and reinforcing steel in medical devices. Some have even experimented with embedding quasicrystals in anti-counterfeiting tags for artwork, leveraging their distinctive patterns as a form of atomic fingerprinting. So, what does the future hold for quasicrystals? Are we on the cusp of a revolution in material science, or will these peculiar structures remain confined to academic curiosity? The debate continues, and opinions vary widely. What's undeniable, though, is the sheer joy and wonder they inspire among those who study them. As Sprinkle put it, quasicrystals are fascinating from every angle, from the mathematics of aperiodic tilings to the physics of superconductivity and the chemistry of alloy formation. They bring together mathematicians, physicists, chemists, and even artists in a shared quest to uncover their secrets. Sun sums it up beautifully. Quasicrystals are like the platypus of materials. They're not necessarily better than anything else, but they're utterly unique. They remind us that nature still has plenty of surprises left to reveal. So, dear reader, where do you stand on the quasicrystal debate? Do you see them as a scientific oddity or a hidden treasure waiting to be fully understood? Share your thoughts in the comments below.